We've now seen a number of situations where we can use statistical tests in order to help us draw conclusions about our data. Some of the results of these tests have been quite important. For example, we were able to show that we have strong evidence that the mean body temperature is not 37 degrees Celsius, which was a result that held for more than 100 years. But any powerful tool must be used responsibly. In this video, we'll talk about potential pitfalls that can occur when working with statistical tests of hypotheses, and how you might avoid them. Here's our first piece of advice. Be careful not to misinterpret p-values. Okay, that might seem pretty obvious, but it's incredible how often it's done. Remember from a previous lecture, what a p-value does not tell you is how likely it is that the null hypothesis is true. But that's a very common misinterpretation. As an example, when we were comparing the mean body temperatures to the established value of 37 degrees, the p-value doesn't tell us how likely the mean body temperature is to be 37 degrees. What it does tell us is how likely it would be to get the observed data that we got if it really was 37 degrees, and then we can assess whether our null hypothesis is a reasonable assumption. Remember that a p-value is a measure of the strength of the evidence. That's pretty valuable, so report the p-value. That might seem obvious too, and it's kind of old-fashioned, but you'll often see reporting that says there was a statistically significant difference, p is less than 0.05. Well, having a p-value smaller than 0.05 is interesting, but just how much smaller than 0.05 was it so that we can actually assess the strength of the evidence? Saying it's 0.03 is good. Then we know that the evidence is only moderate. Our second piece of advice is that data collection matters. No sophisticated testing can correct fundamental flaws in the data collection process. If the sample wasn't randomly chosen, or we haven't controlled what we could, or we haven't randomly assigned treatments to subjects, then we can expect to have bias, confounding, and we won't be able to make causal conclusions. Our next piece of advice, always use two-sided tests. Okay, not always, but unless you're really sure a priori that you're only interested in one direction and that other direction is of no interest whatsoever, then you should use a two-sided test. Here's why. Imagine we're testing a mean. So let's say our null hypothesis is that the mean mu is equal to some value. We'll call it mu star. And we calculate our test statistic, and we get some value. We'll call it t star. In the one-sided case, suppose the alternative is that mu is greater than mu star. Our p-value is this shaded area, the probability of getting a value more extreme than what we got, which in this case is greater than what we got. For the two-sided alternative, where mu is not equal to mu star, more extreme than what we got includes both tails of the distribution, both the values that are bigger than t star and the values that are less than negative t star, since both are more extreme than what we got. So as a result, the p-value for the one-sided test is only half the p-value of the two-sided test. So for the one-sided test, we're more likely to get a significant result. Would that significant result be meaningful? Not if we really should be doing a two-sided test. Taking a look at your data and seeing whether it's larger or smaller than what you expect, and then deciding whether you should do a one-sided or a two-sided test is cheating. Next, statistical significance is not the same thing as practical significance. What that means is that just because we see a statistically significant result doesn't mean that it's meaningful in a practical way. To illustrate this, let's look again at the example of flipping a beer cap. We're interested in whether or not the beer cap comes up 50% reds. Imagine these three sets of data. We got 6 reds and 10 flips, that's our first set. In our second set, we got 58 reds and 100 flips. And our third set of data, what we actually got, 576 reds and 1,000 flips. If we calculate the test statistic for each of these, we get 0.63 for the first data set. That's a reasonably likely value from a normal distribution. We get 1.6 for the second set, also a reasonable value near the center of a normal distribution. For our third data set with 1,000 flips, we get 4.81. By our empirical rule, 99.7% of the data is within 3 standard deviations of the mean. That means within +3 to -3 on a standard normal curve. 4.81 has to be way out in the tail and a very unusual value. But effectively, our data were all the same or very similar. Each of the data sets had very close to 60% reds. So why are these test statistics so different? Well, don't forget that the test statistic has n, the sample size, in it, and that can make a big difference. When we calculate the p-values, we get a large p-value for data set 1, a reasonably large value for data set 2, certainly not small enough to reject the null hypothesis. But for data set 3, we get an extremely small p-value, so we have extremely strong evidence that the proportion of times a beer cap comes up red is not 50%. What this example illustrates is that very small effects can be highly statistically significant when a test is based on a large sample. But that doesn't mean it's practically important. We have to make that decision based on the context. To flip that around, lack of significance doesn't necessarily imply that the null hypothesis is true. We could get a test with a large p-value, so it's not significant because the sample size is too small, or maybe there's just too much variability in the data to be able to detect a difference. So maybe we just don't have enough power. In addition to possibly not being associated with a practically meaningful result, remember that small p-values can happen for a number of reasons. They can happen by chance. They can happen because there were problems related to the data collection. For example, there could have been lack of randomization. They can occur because there were violations of the assumptions underlying the particular test of significance we're using. Or they can happen because the null hypothesis is false. Typically, with a small p-value, we conclude that the null hypothesis is false, but we need to be careful that none of these other reasons are why we got a small p-value. When dealing with data, there is always variability in the associated uncertainty, and it is important to understand both the strengths and limitations of statistical procedures. Because by chance, every now and then unusual data will be observed, we can get a significant result in a hypothesis test, even when the null hypothesis is true. And if multiple tests are carried out, we expect that some of them will be this unusual case. Suppose we have a significance level of 0.05. Then we'll reject the null hypothesis anytime we see a p-value that is less than 0.05. What that means is 5% of the time when the null hypothesis is true, we'll get data that are unlikely enough to reject the null hypothesis. So be suspicious when you see a few significant results when many tests have been carried out. For example, if there's no significant result for the entire group being studied, it may be tempting to think of ways to divide the observational units into subgroups and see if there's a significant result in any of those subgroups. But in a test repeated on each of 20 subgroups, one would be expected to have a significant result, a p-value less than 0.05. That's not an interesting result, that's just what we expect. Related to this is the concept of data snooping. Here's what you shouldn't do. Take a look at your data, notice 2 groups differ, and then say, I think I'll carry out an hypothesis test to see if they do differ. Such a test is much more likely to be significant than if you were guided by a scientific question rather than the data. The primary hypotheses to be investigated should be specified before any data are collected, not suggested by the data, because otherwise the p-value isn't meaningful. For the tests for proportions and means that we've learned, we require the following conditions to be true. First of all observations must be independent of each other, and we need the sampling distribution of the estimator of the proportion or mean to be at least approximately normally distributed. We say that any statistical procedure is robust if it is not sensitive to the violations in its necessary conditions. For our test, there's no way to get around independence. Our observations must be independent of each other. But the sampling distributions of p hat and x bar, our estimators of proportions and means, are approximately normally distributed by the central limit theorem, which tells us that averages have distributions that approximate the normal distribution for large sample sizes. So how large of a sample size do we need for a test? It's hard to make general rules, but here are some ideas to keep in mind. We'll talk about proportions first. Proportions are discrete. In flipping a coin 100 times, we can only observe proportions of 0 out of 100, or 1 out of 100, or 2 out of 100, and so on. There's only 101 possible values. But the normal distribution is for continuous variables that can take on any value to any decimal place all the way from negative infinity to positive infinity. So because our test relies on the normal approximation for a proportion which is discrete, we typically need larger sample sizes for the central limit theorem to kick in. When the true value of our proportion is 0.5, the sampling distribution of our estimator p hat is symmetric, like the normal distribution. However, when the true value of p is further away from 0.5, say closer to 0 or 1, the sampling distribution of p hat, our estimator, is skewed. Here's, for example, what it would look like for p equal 0.01. In these more extreme cases, we need larger sample sizes for the central limit theorem to hold. Otherwise, we need to use a different probability distribution for the analysis, and the testing procedure that we have that relies on the central limit theorem won't work well. That is, the p-value won't be correct. Turning to tests of means, for these we have the t-test, and the t-test is remarkably robust. It gives p-values that are very close to correct, even for distributions of data that aren't symmetric and bell-shaped. So t-tests are useful even for small sample sizes, except when our data are very skewed or there are extreme outliers, which are both cases when the mean may not be the best choice for a representative measure of the data. Statistical tests should always be preceded by plots and summary statistics, which may indicate any problems with the data, perhaps there are skew or outliers, and illustrate any effect that you are seeking. If you can't visualize something in a plot, you may wonder if it's practically important, even if it's statistically significant. Well, some statisticians are working on very sophisticated procedures. Fundamentally, testing can't correct flaws in the data collection design, so be careful when collecting the data to avoid bias and confounding and the inability to generalize and other consequences of lack of randomization. It's easy to put data into a statistical software package and generate p-values. It's much harder to truly understand them and to assess if they really answer the question you want. But statistical testing works well if you design a study carefully to investigate focused questions and then use tests to assess the evidence for or against your hypotheses.